Welcome back, everybody. Day 2 of our last exponential unit here. We're going to be looking at what we call a logarithm. If you've never heard of a logarithm before, they are directly connected to exponential equations and exponential functions. And hopefully after today you will understand why if you don't already. So a logarithm, which is abbreviated log, it just represents a power. A power, or an exponent is another word for a power. So when you're looking at this expression here, first of all, how do you read this expression? So I would see a lot of people want to say, oh, log 4 of 16 or something like that, but that technically isn't correct. So the 4 is the base of the log. The 4 represents the base of the log, and then the 16 we call the argument of the log. But when you're reading this, you would say log base 4 of 16. So we would say log base 4 of 16. That's how you read it, okay? So the 4 is a base. We're going to read that as log base 4. And then the 16 we call the argument. We're going to say log base 4 of 16. Now, what does it mean? What is, when we read this log base 4 of 16, remember, a log is just a power. So when you're looking at this, it's essentially asking you what is the power of 4 of that base that makes that argument of 16. So a log is really just asking you for a power. So log base 4 of 16 is asking what power of 4 makes 16? Well, what power of 4 makes 16? It's 2. That means that the log base 4 of 16 is equal to 2. Okay, because the power of 2, 4 to the second power, is what gets you 16. And it's that simple. Okay, let's look at a few others just so you can try to wrap your brain around this. Remember, you are looking for a power. So when you're looking at log base 8 of 64, that is really asking you 8 to what power makes 64? Well, that's 2. So this thing is equal to 2. So if 8 to the power of 2 makes 64, 8 to what power would make 1 over 64? That's what the next question is asking, right? Log base 8 of 1/64 is asking 8 to what power makes 1 over 64? Well, that would have to be a negative 2. How about here? Log base 7 of 343 is saying 7 to what power makes 343? What power of 7 makes 343? The third power. So that's equal to 3. Now, if you notice on number 4, there isn't a base written there. So when there isn't a base written, there's an implied base 10. Sort of like when you see an X and you know that there's a 1 in front and you know that there's a 1 in front here. If you don't see the base written here, there's an implied base of 10. So this, oops, I thought I still had my eraser on. This is equivalent to the log base 10 of 1,000. So essentially, 10 to what power is 1,000? What power of 10 makes 1,000 would be the third power, so it's equal to 3. Okay, how about the next one? The log base 7 of 1 is what power of 7 makes 1? Well, that's going to be the 0 power. Remember the 0 rule? Anything to the power of 0 is 1. Anything to the power of 0 is 1. Okay, and then how about this guy? If you want to try it out, it's a little bit of a make you think question. Feel free to pause if you want. Okay, if we were reading this, it says log base 6 of 6 to the 4th. So this is asking 6 to what power is going to make 6 to the 4th power, which even sounds a little weird when you try to read it. So let me write this out for you. This is saying 6 to what power, right? This base to what power is going to be equal to 6 to the 4th power, to the argument. Well, hopefully we can see it now based on what we were doing yesterday, right? If those two bases are equal, don't those exponents have to be equal? They do, which means this is going to be equal to 4. Okay, now if these are a little challenging for you, don't freak out just yet. I'm going to show you a way to do these with your calculator, but hopefully most of this is making sense. Now, most of your calculators have 2 log buttons. Some of the fancier ones have a third option, and Desmos has a third option, which I will get to. But if you're just looking at the home screen of a normal calculator, it's going to have two log buttons. It has the LOG button, which we call the common logarithm, and it has the LN button, which we call the natural logarithm. I'm not sure why that's backwards, but there it is. Okay, so the common log is always base 10. We saw that a second ago. And then the natural log is always base E. And if you aren't familiar with E, E is a lot like pi. It's an irrational number. So, you know, we say pi is about 3.14, but technically it's a non-repeating, non-terminating decimal. E works the same way. We approximate it at about 2.72, but technically it is a non-repeating, non-terminating decimal. It's used often in some finance situations, and we're going to see a couple of those situations moving forward in the unit. But for now, E, it's just like pi. Pi is about 3.14, E is about 2.72, so it just represents a number, okay? So here, a couple of problems with just the common log and the natural log. So when you see the log of 100, as I mentioned before, that's a base 10. So this is really just the log base 10 of 100. So 10 to what power makes 100? Or what power of 10 makes 100? That's 2. 10 squared makes 100. Or how about here? This is really the log base 10 of 10. 10 to what power makes 10? Well, 10 to the first power makes 10, so that's equal to 1. Now, if you look at number 8, if this is the log base 10 of 50, is there going to be an exact power of 10 that makes 50? No, there isn't, which means that this has to be something we would evaluate with the calculator, okay? Well, let me just show you in Desmos. If you go to Functions and then Miscellaneous, you'll see the log button here toward the bottom. Now, I could check the others. If I put in log of 100, it tells me it's 2. I established that, right? Again, I could put in the log of 10. It tells me it's 1. I established that, but those are clear. They make a little more sense. Now, since the log of 50 isn't exact, the only way to excuse me, to get that value is to use the calculator. So we're going to put in log of 50, and we get about 1.698. I'm going to say about 1.7. So this is approximately 1.7. Now that answer should make sense. Think about this for a second. If you knew 10 to the first power was 10, and that 10 to the second power was 100, we were looking for 10 to what power to get us to 50? Since 50 was between 10 and 100, it should have made sense that the decimal that we got here was between 1 and 2, right? We said about 1.7, and definitely closer to 2 than it was to 1, okay? So that's a reasonable estimate. All right, let's look at these natural logarithms. So natural logarithm, again, is base E, which is just a number. So it's a little weird, but this is saying the natural log base E of 1. Okay, so even though you don't see the base of E either, it's a base of E always. So this is saying E to what power makes 1? Well, remember, E is just a number. But what can you raise any number to get 1? We said that a second ago. Anything to the power of 0 is 1, so this is just going to have a value of 0. Okay. This is natural log base E of E. Well, what would you have to raise E to get E again? Well, anything to the first power is itself, which means the natural log of E is just 1. And then here, if this is natural log base E of 20, well, E to what power is going to get you 20? Do you think you're going to be able to raise a non-repeating, non-terminating decimal to a power and get exactly 20? No, which means this would have to be something we approximate with the calculator. Now again, just so I can show you, you could put in the others. So natural log button's right above the common log button. If we put in natural log of, we had 1 first, it says it's 0. We established that. If we put in natural log of E, let me go to my keyboard, it's going to tell us the natural log of E is 1. We established that. Those ones made a little more sense. Natural log of 20 isn't going to be exact. The only way to get this is with the calculator. So if we go and find the natural log of 20, the calculator tells us it's going to be about 2.995-ish. So let's just say this is about 3. Okay? All right, so now, what if we have something like number 12 here, the log base 3 of 40? Right, if this was the log, well, I'm sorry, my marker is really fat because I zoomed in. If this was the log base 3 of 27, this wouldn't be an issue. I know that 3 to the third power makes 27, so there's an exact value here. But this is saying 3 to what power is going to make 40? Well, is there going to be an exact power of 3 that makes 40? No, which means this is something that we have to be able to evaluate with the calculator. Now, if you're using a typical calculator, the log button that's on your home screen, you can't change the base. It's base 10. So if you have a different base here, you're either going to have to, in your calculator, search for a change of base log, but in Desmos, this already exists, and you might have seen it when we were clicking in there before. So if we had to evaluate something like this, I would use Desmos. It's my preferred calculator, but if you have, one of the graphing TIs or graphing Casio, the change of base log is in there somewhere. You're just going to have to search for it. Now, in Desmos, we're going to click on the functions option, and then we're going to click on miscellaneous if we're not already there, and then we're going to see log of, I forget. If we go to functions, go to miscellaneous, so we already used the natural log button here, which was base E. We already used the common log button here. Now if you look right next to it, we have the log base A. If we touch that one, we're going to be able to change the base to whatever we want. So we're going to look for that log base A button. Okay, so here, oh man, got my eraser on. Just bad habits, guys. Okay, so log base 3 of 30. I know that's not going to be exact value, so let me show you again. Functions, miscellaneous, hit the log A button, and now you can see I could type in the base of 3, and then I could put the argument of 40 in there, and it tells me it's about 3.4-ish. So this is going to be about 3.4. And again, that answer should make sense, right? So we know that 3 cubed makes 27, and yesterday in our chart we said 3 to the 4th would make 81. We were trying to figure out 3 to what power made 40, so it makes sense the decimals between 3 and 4. Okay? So we can do the same thing here. Before we go to the calculator, we're looking for 5 to what power is going to make 18. Well, I know 5 to the 1st is 5, and I know 5 squared is going to be 25, so I know my decimal is going to be between 1 and 2, and it's probably going to be closer to 2 because 18 is closer to 25, but I have to use a calculator to approximate this value. So my friend Desmos, functions, log base 5 of 18 is approximately 1.795, let's just say about 1.8. And notice I'm using the squiggly equal to say that that's approximately, and I forgot, 1.8. Okay, let's try this one again. No exact power of 4 is going to make 22. Now I know that 4 squared is 16, and I know 4 cubed is 64. So I know that the power I'm looking for here is going to have to be between 2 and 3. But to get that power, I'm going to have to go to my calculator. So log base 4 of 22 is about 2.2-ish. So let's say this is about 2.2. Okay. Now I didn't use the calculator for these problems up here just because these are exact, and I'm hoping that you know that 8 squared makes 64, but in all honesty, any logarithm can be evaluated with the calculator. So if in the beginning here you were confused, you could still have put in log base 8 of 64 and used your calculator to arrive at that answer. Or if we're looking at this, this crazy one that I said, oh, you try it out. You can put in your log base 6 of 6 to the 4th here, and it's going to tell you that the answer is 4. Okay? So the goal would be to be able to look at some of these and understand, like these first set we did, understand what the values are, but ultimately your calculator could be used to evaluate any logarithm. All right, so far. So now I want you to see a little more of the connection between the logs and the exponentials. So any logarithm can be rewritten in an equivalent exponential form, and this should make sense. So we said in the beginning there, if we had the log base 8 of 64 equal to 2, it's because 8 to the 2nd power was equal to 64, right? It's because the 8 to the power of 2 made 64. These are two equivalent ways to say the same thing. These things are equivalent. 8 squared makes 64. this log base 8 of 64 being equal to 2 is because 8 squared makes 64. So we can go back and forth from a log form to an exponential form. Just going to replace the 8, 64, and 2, the exponent, the argument, and the base with some variables. So if I have any log expression, let's say we have the log base b of a, it's going to be equal to some power, let's call it x. So this is going to be true because if I take that base of b and I raise it to the xth power, it's going to give me that argument of a. Okay? So we should be able to take anything in log form and rewrite it in exponential form. Any log equation and rewrite it as an exponential equation, or vice versa. And this is going to help us solve exponential equations that can't be rewritten with common bases like we saw yesterday. Okay? So let me just... well, I can leave it there. Let's practice, okay? If we're going to go from one form to the other, keep in mind here, going from one form to the other, that the base of the log is the base of the exponent. So the base of the log will be the base of the exponent, and the exponent in the exponential is the answer to the log, right? The exponent of the exponential form is the answer to the log. Okay, so we're going to just practice rewriting, not doing any work here, trying to solve anything, just going from a log form to an exponential form, or vice versa. So saying that log base 2 of 32 equals 5 is the same thing as saying that 2 to the 5th power equals 32. Okay, the base of 2 is still the base of the exponent, and the exponent here is the answer here. Okay, log base 3 of 9 equals 2 is equivalent to 3 squared equals 9. And I think that these are intuitive because we know the connections between the numbers. All right, log base 5 of 125 is 3 because 5 cubed is 125, so those are equivalent. Now going this direction tends to be a little bit harder because we're introducing a log, and it's not as intuitive as the exponential. But if we wanted to rewrite 12 squared equals 144 as a log, if the base of the exponent is 12 here, the base of the log is going to be 12 here. And remember, the exponent becomes the answer. So it's going to be log base 12 of 144 equals our exponent, our power of 2. Or here, 6 cubed equals 216 is equivalent to the log base 6 of 216 equals 3. Base is the base, the exponent's the answer. Okay, or here, 3 to the 5th equals 243 is equivalent to log base 3 of 243 equal to 5. Okay, so this is a concept that we're going to use to solve. So let's look at number 19 here. Yesterday, if I gave you like, okay, 3 to the x equals 9, well, this is no big deal because I know that 9 is 3 squared, and if those exponents are equal, if those bases are equal, those exponents have to be equal, right? If I'm looking for 3 to a power to give me 9, that's not a big deal because I know there's a power of 3 that makes 9. But if I'm looking for 3 to some power to make 10, is there going to be an exact power of 3 that makes 10? No. Well, that's where the logarithm comes in, right? We are looking for a power. We're looking for a power. That's exactly what a log is. A log is a power. So if I rewrote this in log form, this would be the log, base of the exponent is 3, base of the log is 3. So the log base 3 of 10 is that power that we're looking for. So if I rewrite this in log form, it's solved, right? X is by itself. That was the goal here. Now all I have to do is evaluate that expression using my calculator. So I'm going to type in the log base 3 of 10, and it's going to tell me that it's about 2.1, which makes sense because 3 squared is 9, so the decimal should have been a little over 2. So what did I say? 2.1. Or if you want to keep the 0.09, if it doesn't tell you where to round, the more you keep on your decimal, the more accurate it's going to be. I don't know, tenths, 100th place is usually pretty standard. It's whatever. So what we want to do here is, if necessary, we're going to get the base of the exponent by itself. So isolate the base of the exponent, and I'll show you that in the next problem. And then we're going to try to rewrite our exponential equation in log form, and we might still have to solve for x from there, but basically we're going to be using Desmos or calculator to evaluate. Okay, so we have an answer here. Now if you notice number 20, the base of the exponent, the 5 to the x power, it isn't by itself. When I rewrite in log form, log base b of a equal to x, I've got a spot for 3 pieces. For the base of the exponent itself, and then the answer here, which is our argument, I don't have anywhere to put this 2. So I have to start this by getting rid of that 2. Well, how do I get rid of multiply by 2? Divide both sides by 2. So we're going to start this by dividing both sides by 2. That's going to make this cancel. And now I have my 5 to the x power equal to 128 divided by 2 is going to make 64. Now again, there's no exact power of 5 that's going to make 64. So I can't just rewrite that side and cancel the bases. But if I'm looking for a power that isn't exact, the log is the power. So I'm going to rewrite this as the log base 5 of 64. That is my power that I'm looking for. That is my x that I'm looking for. So now I just put that into my calculator. So we're going to say log base 5 of 64 is about 2.58. So about 2.58. And you know, the great thing is if you wanted to check your answer, you could absolutely plug that back in. It's not going to give you an exact match because we rounded the answer, but it's going to verify that you did that correctly. Okay, now look at number 21. Number 21 has a base that is a little different, right? Base of 5, base of any other number, we're going to use the common log. But when the base is e, we're going to use the natural log because natural log is already base e. So with base e, use natural log. Okay, and you're going to see why in a second. If I go to rewrite this, instead of common log, I'm going to say natural log, base of the exponent, base of the log, of 42 is my power, x. Well, natural logs are already base e, so this is the same thing as just saying natural log of 42 is equal to x. So my calculator is really just a couple buttons here. I'm going to hit natural log of 42. It's 42, right? Yep, so my answer is about 3.74. This is about 3.74. Okay, now you can use the common log if you want. Let me just show you an alternative here. If I use the common log, base e of 42 equal to x, this should still work. It's just preferred to use natural log because natural log is already base e, but this will still work. Hopefully Desmos likes it. So if I went log base e of 42, gives me, yep, same answer, 3.74. Okay, so you could do the same thing. It's just preferred to use natural log when it's base e because natural log is already base e. But this works too. Up to you, I suppose. All right, now, oops, let's continue. So here, we've got a little extra piece in the exponent. That's okay. It's still just a base, an exponent, and the answer here. So let's rewrite this. I know there's not going to be an exact power of 2 to make 30, so I can't make those bases cancel. So I'm going to say the log base 2 of 30 is this time going to be equal to not just x, but 2x. That means if I want to solve for x, I'm going to have to take an extra step here. If x is being multiplied by 2, I'm going to have to divide both sides by 2. So x is going to equal, this will be exactly log base 2 of 30 over 2. You can't actually divide that number 2 into the base or into the argument because this represents some decimal, and divided by 2, I don't know what that's going to be, so I have to type this into the calculator as is. So x is going to be approximately, let's type it in here. I'm going to make a fraction first. In the top of the fraction, log base 2 of 30, and then I'm going to divide that by 2, and I get about 2.45. So 2.4, was that 45? Yes, okay, sometimes I second guess. All right, let's try again. Now this is sort of like the second one we saw. If I wanted to rewrite this in log form, I have a spot for the base, for the exponent, for the 25, but not for the 7. So I'm going to have to move the 7 first because it doesn't have a spot in the log form. So how do we get rid of a plus 7? Well, we subtract 7. So that's going to leave me 3 to the 4x power equal to 18. And now there's no exact power of 3 that makes 18, so I'm going to rewrite this in log form. So I have log base 3 of 18 equal to 4x. And now x isn't by itself, it's being multiplied by 4, which means I'm going to divide both sides by 4. So x is going to be equal to exactly log base 3 of 18 over 4, and that is approximately, let's find out. Log base, it's not going to let me make a fraction first. On the top of the fraction, log base 3 of 18, and then that whole thing gets divided by 4, and it is approximately 0.66. 0.66. Again, at any point if you want to check your answer, you can plug it back in. So let's do that here just so you can see. And we rounded the answer, so it's going to be close. So if I put in 3 and I raise it to the 4 times 0.66, and then if I add 7, it should be pretty close to 25. Now it's a little over because I rounded my answer up a little bit, but you can still verify that you're doing this correctly. Okay? All right, one for you to try if you want to give it a shot. Feel free to pause if not. Let's continue here. So this plus 1 is not like the plus 7 in the last problem. It's all in the exponent here. So I have a base, an exponent, I have the 50. This can go straight to log form. So I'm going to rewrite this as the log base 7 of 50 equal to x plus 1, which means if I want to solve for x, I'm going to have to subtract the 1 over. Now be careful, I can't just take the 1 from the 50 because the 50 is attached to the log. So I have my log base 7 of 50, and from that decimal I am subtracting 1. So that is my exact answer. Approximately how much is this? Let's find out. So my log base 7 of 50, and then afterward I want to subtract a 1, so it's about 1.01, approximately 1.01. And there it is. Okay, so we can use logs to solve exponential equations, and we can also use the rewriting option to solve log equations. Sometimes our log equations can just be evaluated. Look at number 24, for example. That's technically a log equation, but we don't have to do any solving because x is already by itself. So all we're doing is evaluating what we have on this side of the equation. Now if x is somewhere where we got to get rid of something, then we're going to rewrite an exponential form to solve. Okay, so we're just going to evaluate if x is already alone. That would be wonderful. But if x is not alone, then we're going to rewrite an exponential form to solve. Okay, so for example here again, x is already by itself. I don't have to solve for x, I just have to evaluate. So we're going to go straight to the calculator. So x is going to be approximately, let's see, 4 cubed is 64, so it's going to be less than 3, right? Let's see, log base 4 of 50 is about 2.82. 2.82, easy. Right, if only everything could be that simple. Same thing on number 25, right? This is already solved. X is by itself. So if we put in the log base 4 of 0, it's going to say undefined. That means that this equation doesn't have a solution. So this is undefined. That means there is no solution to this equation. Now why is this undefined? So think about what this is saying. This is, if I put this in exponential form, right? If I rewrote this in exponential form, this is saying 4 to some power is going to make 0. Well, is there any way to raise 4 to a power and get it to be 0? Think about that, right? If I raise 4 to the power of 0, I'm going to get 1. If I raise 4 to any positive power, let's say 2, then I get 16. If I raise 4 to a negative power, then I just get a fraction of what I got with the positive power. In no way am I going to be able to raise a number to a power and get it to be 0. Okay, I can make the fraction smaller and smaller by making the exponent smaller and smaller, but no matter how small it gets, I still have a fractional value here. So since it isn't possible to raise a number to a power and get 0, then taking the log of 0 is never going to work. right? This will never be possible. So since, let me change colors here, since you can't raise a number to a power 4 to, let's just say 4 to some power and make 0, then, well, I want to say this more general. Since you can't raise a number to a power to make it 0, whenever you have a 0 in there as an argument, it's not going to be possible. There will not be a solution to this equation. So this equation has no solution. The calculator told you, though, that was undefined, so that's your clue there, all right? And we're going to talk more about restrictions when we get to functions, okay? Now, if you look at 26, 26x is not by itself. Can't go straight to the calculator with that one. So in this one, we're going to rewrite this. If I rewrote it, this would be 5 cubed is equal to x. Well, now that it's rewritten, x is solved for. So this is just 5 cubed, which is 125. No big deal. Right? All right, moving right along. How about this guy? X, again, not by itself. So if I was to rewrite this, remember, natural log is base e. So if I was to rewrite this, this is e squared equal to x. Well, now x is solved for, so I can evaluate this with my calculator. What is e squared? E squared is about 7.34. So 7.34 is my solution there. Okay. Here, x not by itself has to be rewritten, so this would be 8 to the 2/3 power equal to x. Well, now that it's rewritten, x is solved for. So this is 8 to the 2/3 power. Now you can use your calculator for that. I'm hoping you don't have to, but if I raised 8 to the 2/3 power, I get 4. Why do I get 4? Remember that 8 to the 2/3 power, that is the cube root of 8 squared. The cube root of 8 is 2, and 2 squared makes 4. So hopefully you remember that. If not, that's okay. Your calculator can evaluate 8 to the 2/3 power. All right, how about this guy? This looks a little scary, maybe. Again, x not by itself, so we're going to rewrite this. Rewritten, it becomes 3 cubed equals x plus 1. Well, this isn't so bad. 3 cubed is 27. So if 27 is equal to x plus 1, I just got to subtract that 1 over, which means my solution here is 26. Hopefully you're finding that these aren't too bad. They're pretty manageable. All right, how about this guy? Remember, when we don't see the base on the common log here, that this is base 10. So this is log base 10 of x squared equals 2. So if I rewrote this, 10 squared, the base, the exponent, equals the argument x squared. So if we have 100 equal to x squared, what does x have to be? Well, we know that we can take the square root of both sides to undo that. So x is going to be equal to, make sure that when you take the square root, it's not just a positive 10 squared that makes 100, it's also a negative 10. So this is plus or minus 10. Two solutions on this guy. That can happen. Okay? How about here? X not by itself, so we're going to rewrite. This becomes 4 squared. 4 squared equal to x minus 3 over 2. 4 squared is just 16. So if I want to solve this, I'm going to get rid of division by 2 over here by multiplying both sides by 2. Multiply both sides by 2. That cancels these out. So 2 times 16 makes 32 on this side, and I still have x minus 3 over here. Now I'm going to add 3 to both sides. That makes that go away. So x equals 35 is my solution. And again, at any point you can plug these in to check just to make sure. Let me just show you. So on this one, if I wanted to check log base 4 of, in the parentheses, I'm going to put in 35 minus 3 on the top, 2 on the bottom, and when I put that 2 in there, it gives me the answer of 2 that I know I was supposed to get. Good. Okay, this is the last one. Are we really toward the end? Okay, good. Last one. So last one, again, x not by itself means we're going to rewrite this. So we have x squared equal to 2x plus 3. So this is a quadratic. I'm going to move everything over to one side to make a 0, and then this ends up being factorable. What are the factors of -3 that make -2? -3, positive 1. So if this factors into x minus 3 and x plus 1, then I get two solutions. X equal to a positive 3, and here x equal to a -1. So here we go, two solutions. Now let's just verify. Move this calculator over here. If I put in the log base 3 of 2 times 3 plus 3, it gives me 2, which is what I was supposed to have. And then if I try that again, if I put in the log base -1 of 2 times -1 plus 3, it's going to say it's undefined. So -1 as a base of a log is no good, and it has to do with our exponentials not being able to make 0. So remember this question up here? We said there's no way we can raise something to a number and make it 0. If it can't even get to 0, there's no way it can get to a negative. So this probably isn't really clear right now, but when we get to functions, I'm going to reinforce this. But you can't take the log of a negative number. The base of a log can't be negative. You can't take the log of 0. The base of the log can't be 0. There are restrictions with logs because there are restrictions with exponentials, and the two are directly connected. So remember, anytime you have a restriction in your situation, you can get an extraneous solution. So this is an extraneous solution. And again, we're going to talk more about why we have these restrictions when we get to functions. This is the only one that works here. But basically, we can't take the log of 0 or natural log of 0, and the base of log or natural log can't be 0 or negative. Okay, so anywhere I put a 0, I can't take the log of 0 or the natural log of 0. I can't take the log of a negative or natural log of a negative, and the base of your log or natural log can't be negative, can't be 0. All these things are restrictions, and again, when we get to the functions, it'll be a little more clear as to why. So when you have zeros or negatives in your argument or in your base, that's no good. I guess that would be a more concise way to say this. Now that I put it out loud, the base and or argument of log or natural log cannot be 0 or anything negative. That works much better. There we go. I'm sorry if you already wrote that and had to erase it. Good thing you can pause. All right, I think that is enough for one day. I'm sorry, you were probably still writing that. So I think that's enough again for one day. We're going to continue